All right. صباح الخير. I hope everyone's doing well. I thought it would be nice and not only we have a recording, but we kind of have a live audience for those who are able to. طبعا this is all going to go up. ما حنسوي شيء extra for those who can't access it right now. So hopefully you guys have looked at some of the videos, and I put these videos for my students as well so that they can get an idea of what we're going to be working on in the lecture. So what we're going to be doing in the next, inshallah, in the next week is every day تقريبا, I'm going to be recording a lecture and I'm going to be uploading it. Again, يحضر. We're going to be doing this at the same time. And what we're going to be doing is looking at the basics of radiation physics, and we're going to be looking at the basics of the use of radiology in dentistry. So all the basic intraoral techniques, all the basic extraoral techniques that you will be using in your practices, inshallah. But to understand these things, we first need to understand what is it that we're using? What is this technology of imaging that we are using? And we're going to be starting off with physics. I'm not going to get too deep into, let's say, the nitty-gritty of things. And the reason is that I'm only going to be using physics that are going to be useful to you as a clinician. Okay? All right. So let's start. I apologize that my presentation is on a PDF, but هنتصرف. I'll put all the videos in the video format. All right. So first of all, what is this technology that we are using? Basically, we are trying to look inside of the human body using two-dimensional imaging. And we have to remember that we are using two-dimensional imaging. What does two-dimensional imaging mean? That we always are missing that third dimension. But we are looking inside of the image, we are looking inside of the human body using two-dimensional imaging of a three-dimensional object, right? So anything that we're able to, it's sort of revolutionized the way we do medicine, we've done dentistry, and it's a major tool in diagnosis and in practice. So what is sort of, أنا دائما استخدم this image right here to explain sort of خلينا نقول, what is it? What are the factors or what are the main players when it comes to taking radiographic images? The first thing is obviously your camera or your X-ray tube, which is going to produce your images. That's number one. Number two is the object that you're going to be imaging. It always plays a role as well. And number three is your receptor, which could be plain film, it could be a digital receptor, whatever it is that is receiving that information, and then you're able to see it with your own eyes. So these are the three main elements that we talk about whenever we talk about radiographic imaging. Whoops, I'm sorry. So when we talk about X-rays and when we talk about ionizing radiation, we want to start from the very, very beginning and think about, we're going to go back لسنة أولى, we're going to go back to high school, and remember this all starts within the atom. So the atom is made out of a nucleus, and it's made out of an electron cloud that kind of circulates around this nucleus. Inside the nucleus, we have protons and we have neutrons. And outside of that, we have electrons. The nucleus is usually a positive force, which is, of course, the protons are positive. The neutrons have no charge. And then we have electrons, which are a negative charge that go around the atom. Most of the atoms that are around us, what you breathe and everything that we touch, are stable atoms that are in stable forms in the form of molecules. But it is going to be the main thing that we're going to use to understand how we produce radiation. So again, we have negative electrons and positive protons, and we have neutrons that don't have any charge. And then, of course, one of the most important things is this binding energy that we have. So why aren't electrons floating everywhere? They are bound to that nucleus by forces, and these forces are going to be very important to understand. Are going to be very important to understand when we are talking about the production of radiation and energy, correct? So these electrons are bound to the nucleus with certain forces. And these are the forces, and these binding forces are this binding energy is what we're going to be using to create radiation. So this is just very basic revision of the classic physics that you usually have. So what is radiation? What is radiation at its essence, at its core? What does it mean? So basically, radiation is the transmission of energy through space, and they can be in two types. So radiation is an energy, basically. والenergy هذا يمشي through space. There's two types. There's one called particle, and the other one is called electromagnetic. So particle energy is not something that we're going to be talking about, but particle energy is when the particles or pieces of the atom itself, so alpha particles, beta particles, are actually moving through air. That's kind of nuclear, that's nuclear medicine kind of thing, nuclear physics. We're not going to be talking about that. What we're interested in is the movement of energy through space through what we call electromagnetic energy, right? And that is everything from the simple light that you see around you. It is microwaves, it is radio waves, television rays, and of course, X-rays. So what are electromagnetic waves? So electromagnetic radiation or electromagnetic energy is the movement of energy through space. So this is, again, energy movement through space in a combination of an electric and magnetic field, right? So it is, they have a field. Every single electromagnetic wave has a direction and has a wavelength, and it has a certain energy. So if you can look over here, you have two fields, a magnetic field, and perpendicular to that, you have an electric field. And again, this is what forms every single type of energy that is around you, whether that's light, visible light, or whether that is radio waves or any type of energy that moves through space. So you guys might be familiar with this particular graph. I'm sure you've seen it before. And if you look at electromagnetic energy, you can see that we have very low energy electromagnetic waves. And then as we move along this graph, you can see that the energy increases. But what do you notice with the increase of energy? You also notice that the frequency and the wavelength, اللي هي المسافة ما بين الpeak of the wave to the other peak of the wave, هذه المسافة, as you have more energy, decreases in size. So the least amount of energy, for instance, is in radio waves, right? These are long frequencies that can move very long distances, correct? And then as we move forward, you start seeing a little bit more energy, smaller distances or smaller wavelengths in microwaves that produce heat. This is the main thing that produces heat. And then we have infrared, which is now becoming an area where we have visible light, correct? Which starts from this region right here, from infrared all the way up to at a point where we get ultraviolet, then you see higher energy, and you have very small, you're starting to get smaller wavelengths, okay? So hopefully everybody understands that. Where does X-rays come in? Now what we're talking about, now when we look at these radiation, this area of radiation, or now that we look at this energy level, these are called penetrative electromagnetic waves. So all of these waves right here don't really penetrate, are not penetrating. So if somebody stands in front of light will not penetrate you and go the other way, right? The same thing as microwaves. It will be absorbed, correct? But it won't penetrate. Now, X-rays, and as we move forward, gamma rays and alpha and beta particles, those are penetrative. These are electromagnetic waves that have so high energy that it can actually penetrate through solid material. So where do we live? The area we live in is right here. X-rays وإحنا طالعين. So we have very high energy with low wavelengths. So هذه بس عشان تفهموا طبيعة X-rays أو طبيعة X-rays اللي احنا هنستخدمها to produce images. So when we talk about, we can never talk about electromagnetic waves or energy without talking about quantum theory. So in quantum theory, basically says it considers electromagnetic radiation. So an electromagnetic radiation that we just talked about, or electromagnetic, it considers it as small, discrete bundles of energy that is called photons. Okay, so we're going to use the word photons a lot in the next little while. So what are photons? They're basically small bundles of energy, right? Electromagnetic energy that have a certain energy and have a certain wavelength, okay? And this, and the physical sort of equation that it looks like here is that the energy of these photons, these little bundles, ودائما نستخدم هذه squiggly line right now. You'll see me using it a lot. This squiggly line means that this is a photon. This means it's an electromagnetic wave. It has a wave كده وبعدين لها اتجاه. هتشوفوها دائما in في الرسمات حقت radiation. So photons, the energy of a photon equals a constant, ثابت, 1.24, على wavelength. What does that mean? إنه الموضوع هنا ما هي علاقة طردية، علاقة عكسية. Energy of a photon علاقتها عكسية مع wavelength. So if we go back here, it makes sense, right? كل ما قل wavelength زاد الانرجي، وكل ما زاد wavelength قل الانرجي. Does that make sense? So هي علاقة عكسية. كل ما زاد الانرجي نقص wavelength. كل ما نقص الانرجي زاد wavelength. Okay? So in general, it's important to know what a photon is. A photon is a small discrete bundle of energy, and we're going to be using the word photons a lot. All right. So now let's get into that. What's sort of the basic physics or basic knowledge that you have to sort of understand about what are X-rays? What is this that I'm using to create an image? And where is this all produced? This is produced inside of your X-ray machine. So if you've ever taken an image for yourself, for your patients, or you are a patient yourself, whenever you do one of these small X-rays that goes inside of your mouth, and then they put in sort of an X-ray tube to come right near your teeth. This is the X-ray tube or the X-ray machine that we are using in dentistry. So what happens in the X-ray machine? We are actually producing X-rays. We are actually producing photons, okay? Which brings us to what's inside of your X-ray machine? What is it? What do we have in it? How is it produced? What is produced and how? So the main two things you have within your X-ray machine is something called the X-ray tube. The X-ray tube is something that is seen in every single X-ray machine, whether that is an intraoral machine, whether that's a panoramic machine, whether that's a chest X-ray machine, it doesn't matter. Every single X-ray machine has something called the X-ray tube. And the X-ray tube is basically where we form photons or where we form X-ray radiation. Okay, this is where all of that happens. And we'll talk about it in detail in a second. This X-ray tube is always connected to a power source. So it has to be connected to the electricity and to a power source, which will power this X-ray tube. All right. So now let's look at this X-ray tube right here. Here it is. Here's your X-ray tube. You can see that there's that it's all covered in a glass in sort of like a glass casing. And let's take a look at what it looks like. So there's two sides to an X-ray tube. The first side is a cathode, all right, a cathode. And the second part is an anode. The cathode is a negatively charged side, and the anode is a positively charged side of the X-ray tube. In the cathode area, what we have here is something called a filament. And in the anode, we have on the other side, on the anode, what we have is the other side, which is, we'll take a look in a second about what it looks like, which is basically the receiving side of the machine. So on this filament, the filament is made out of tungsten, and also the receiving end here is also made out of tungsten, right? So filament, we have in the cathode a filament, a tungsten filament, and in the anode we have a target, or we call it the tungsten target. Okay, I hope that's clear. So how do we produce radiation at this level? This filament over here, this tungsten filament over here, basically is heated to a point where it's heated so much where we actually boil off electrons. These electrons these are free electrons, then move from the cathode, because it is negatively charged, to a positively charged target so fast that it then hits the target and produces photons. And then it produces photons. And we'll take a look at how that happens. But I just want you guys to تخيلوا el big picture here, okay? So you have a filament, a tungsten filament. It's made out of a lot of very, very big atoms, okay? These atoms have a huge electron cloud around it. We'll take a look at that in a second, okay? What happens is we heat this atom, this tungsten atom, so much that we boil off the electrons that are surrounding it, right? And they kind of float off, right? And now we create a charge, a positive charge, to allow those atoms to very quickly at very high speed, move from the filament, the negative side, to the positive side. They hit the target, the tungsten target here, and what it produces is X-ray photons. These X-ray photons, these are the electromagnetic waves. So now we're going to take a closer look at how that actually happens. So let's take a look at this in detail. Here's your cathode, right? Your cathode, which has the filament. الفيلمنت هنا واضحة أكتر. It is a filament right here. It looks شكلها كده زي الكويل, right? And what we call here, this is an electron focusing cup. هذه details شوية بس عشان تفهموا if you ever see this يعني. It's a focusing cup where it focuses these boiled off electrons in a cup right here. And then on the other side is your anode, where you have a tungsten target. And this tungsten target is attached to what we call a copper stem. And remember, this tungsten target becomes very, very hot, very heated, but we need something to dissipate that heat. So what we do is attach it to a copper stem. طبعا كل هذا is all covered up in a glass envelope, and there's a vacuum in here because we don't want these electrons to be hitting anything else. No air particles, nothing except for the tungsten target, so that we're able to produce useful X-ray beams, which is right here. Okay, so I hope everybody sort of understands this basic concept. All right, so let's talk about our tungsten. This is our source of electrons. So these are our source of electrons. This is what a tungsten atom looks like. So you can see here that this is a big chunky atom, okay? And that's exactly why we use it, because it has a high anatomic number. Because it has a high atomic number, it has a lot of electrons that we can use, and it will produce more photons when they're heated. The other really important thing is, obviously, when we heat this metal, we don't want it to melt. We are going to heat it to a point where we get electrons to fly off of it, but we don't want to disintegrate it, basically, and cause it to melt. So it has a very high melting point. And the other thing that it has very good thermal conductivity, which means any heat that it absorbs, بسرعة, and conducts it to another metal. And this is why we had the copper. As I said before, it's attached to copper, and we want it to dissipate the heat without it actually ruining the machine. So high atomic number, and you can see it visually here. We have these, look at all of these electrons. You can see the number of electrons here are quite big. And you can see that these are the binding energies, and you'll see why this is going to be really important in a second. The binding energy is going to give us the electromagnetic wave that we need. So anyway, again, why tungsten? This is a question that can be asked in examinations. It can be asked in board exams. Why do we use tungsten in X-ray tubes in dentistry? These are the reasons: high atomic number, high melting point, and a very high thermal conductivity, because it transfers heat to the copper stem. Okay. All right. So زي ما انتم شفتوا هذا كله this X-ray tube is connected to an X-ray source. Is connected to a power source. Why is it connected to a power source? وإيش فايدة الpower source هذه? Two things. The first function is to heat the filament. And how am I going to heat the filament? بالكهرباء, basically. So when I heat it, what happens is the power source is going to come in and heat the cathode to generate or to boil off these electrons. The second thing is, عشان after we boil off these electrons, remember, I want these to move very fast to hit the target to produce photons. How do I make it move very fast? إني I create a potential. أسوي فرق potential between the two sides, so that the electrons can move from the negative cathode to the positive anode. Insane? So to establish a high voltage potential between the anode and the cathode, which allows the electrons to move very quickly from one side to another. So that's the power supply. So what does that power supply look like? It's not very important, but it's good for you to be able to see it. Well, I'm going to tell you why these are important in a second. So here's your X-ray tube. Hello, here's your filament, and here's your target. Your electrons are going to boil off from here, and they're going to hit your target on the other side, correct? Both of these sides are connected to an X-ray source, to a power source. The power source عندنا واحد خصيصا to boil off electrons, or to heat the filament to boil off electrons. And then we have another one over here that is going to create an action potential between these two sides, so that we have a strong positive and a strong negative for the electrons to move from one side to another. Now, ليش هذه الأشياء مهمة؟ ليش أنا لازم as a dentist ولا أفهم هذه الأشياء؟ لأنه what happens here is these things are things that we can select and we can actually change when we are taking our X-ray images, because this is connected to a KBP selector and an MA selector, which we're going to talk about in a second, which is tube electricity, or tube potential or power and energy. And we're also going to be looking at the MA, which is the milliamperage. So all of these things, عشان تكونوا فاهمينها, this is what powers your machine. وإحنا لنا التحكم في إنه نزود ونقلل من هذه الأشياء depending على الحالة اللي عندنا. Okay? All right. So again, very quickly, we have two major power supplies. The first supply is going to supply your filament. ليش? To heat the filament. عشان we can boil off electrons. The second one is to create a potential between the two, so that we can have the electrons move quickly with high energy to produce photons on to the target. I hope that's clear. All right. So let's take a now I'm going to have to show you the video on another screen, because it's so silly that I can't find my actual lecture. So let me change my screen over here to production of X-rays. All right. All right. Production of X-rays. I'm going to just do something here. I'm going to stop sharing for 1 second, and then I'm going to reshare a new screen. Here we go. Okay. Give me a thumbs up if you can see the video screen, if you're still there. All right, excellent. All right, so let's listen to this video. Now that you understood it, now let's try to see it, okay? All right, here we go. The lab setup shown here was designed by Coolidge, and hence it is called Coolidge tube. It contains a highly evacuated glass bulb containing a cathode, which is a tungsten filament, and anode, which is a target made up of metal of high atomic weight. The pressure inside the bulb is maintained at 10 to the power of -6 millimeters mercury. When the cathode is heated by passing a current through it from a low-tension battery, it emits cathode rays. These rays are nothing but electrons. The filament is surrounded by a molybdenum cylinder, which is kept at a negative potential to the filament. This repels the electrons further, and hence the electrons form a fine pencil beam at the center of the cylinder. This pencil beam is also accelerated by the cylinder towards the target. The target is made up of a copper block in which a piece of tungsten or molybdenum is fixed. High thermal conductivity is used to carry away the heat generated to the cooling setup. Here we use copper, which is a good conductor of heat and can take the heat away from the molybdenum metal towards the water cooling system. The target is also tilted at an angle of 45 degrees, causing the electrons to hit at an angle. This will produce the X-rays almost perpendicular to the electron beam. A very high potential of 20 kV is applied between the source and the target. Due to the high potential difference, the electrons are accelerated towards the anode and it hits the metal. When it hits, the kinetic energy is transferred to produce X-rays. The intensity of the X-rays depends on the number of electrons striking the metal target. So, if we can increase the rate of electrons emitted by the filament by increasing the current flowing through the filament, then we can increase the intensity of the X-rays. Okay, so that was just something to visualize what is actually happening. So I'm going to go back to my presentation. Okay. So silly. 1 second. Okay. Won't let me stop. Okay. I just did it. It's not sharing. Okay. Now I'm going to go back to the presentation. All right, here we go. Share. No, it did not share. Stop sharing. 1 second. Share. This one. Share. Okay, perfect. So just to comment very quickly on that, that was a detailed expression of what is actually happening. This summary is exactly what I wanted you to hear, which is the production of electrons on the filament, which then hit the target, which then produces electrons, the photons, and this is all done through the powering of the filament and through the powering of both sides, so that we can get that electron beam that then produces photons. Insane. Okay, so now let's go on to the next little bit. Again, I talked to you about tungsten. And I want you to look at our electrons over here before we move to specifics about the next little part, which is the production of X-rays. So how do we produce X-rays? Now, if we look at the tungsten atom, you can see over here that we have in the center over here, you have your nucleus. And as we go out, we can see these large amount of electrons surrounding it. Now, I like this image here because it shows by color the attachment or the energy binding of the electrons to the nucleus. So the most attachment or the highest binding energy is in the shells that are most close to the nucleus right in the center, correct? As we go outwards, the electron or the electron binding energy قاعد يقل. يعني anything further away from the nucleus حيكون ماسك في النوكليوس أقل من binding energy اللي هو داخل النوكليوس or in the inner shells. And this is going to be important in the production of radiation. So look at the numbers over here. If we look at the binding energy, the K shell is the innermost shell. It is 69 keV, which is kilo electron voltage, right? 69. Versus لما أطلع برا عند ال O, look how the binding energy decreases. It's 0.1. So it's very easy to remove an electron at the outer shell. But removing an electron in an inner shell is going to be very difficult, right? So إحنا الهدف كله من الإلكترون beam إني I can create an electron beam that can hit out other electrons والفرق بينهم produces a photon. So let's see how that's done visually. لأنه لما أتكلم it doesn't make a lot of sense. So let's look at X-ray production. So remember where we are here. Where we are here is we're at the filament, right? We're at the filament. The filament, we boiled off electrons, and now the electrons are going to hit the tungsten. What happens when the electron hits the tungsten? هذا اللي حنتكلم عليه right now. The production of X-rays. What happens to these electrons once it hits the tungsten? So once the electron hits tungsten, there's a couple of things that are going to happen that will give me photons. The first one is the Bremsstrahlung radiation. This is a German word, but this is the first thing that is going to happen. And the only way to understand it is to see a video of what happens. Okay, so now I'm going to stop and I'm going to start again, which is super annoying. Okay, now I'm going to open the video here. Okay, I'm going to switch over. I'm sure I can do this more easy. Okay, I am sharing this. I'm going to stop sharing. Okay, QuickTime Player. So now I'm going to switch over to this. Oh, perfect. I can do it a lot easier. Share. All right. Can everybody see this? Thumbs up if you can. Awesome. All right. So أبغاكم تركزوا في الفيديو. Look at what's going to happen. هيجي من on this side of the video. You're going to see a flying electron. A flying electron is going to interact with this big tungsten atom. Okay, I'm not going to say anything. I want you to look and see what happens. All right, I'm going to play it. There's your flying electron. The flying electron moves out of place. So what just happened here? I'm going to play it one more time. Electron comes in, comes very close to the nucleus. It completely changes direction and emits energy. So what happened here? أنا أكثر شيء أحب لما نشرح ده للطلبة أبغاكم تتخيلوا معايا سيارة ماشية مرة بسرعة. أوكي؟ ماشية مرة بسرعة. وفجأة اللي بيسوق يغير اتجاهه very quickly. احنا نسميه بالسعودي I'm not sure what you guys call it. يفحط. أو بالكويت يقول يقحص بالسيارة. Right? يغير اتجاهه. What happens لما الواحد يفحط بالسيارة? A few things happen. يحصل sudden stoppage of the car, and this kinetic energy that the car had can change into what? Can change into heat, correct? By مثلا التايرز تنحرق, you can see complete change in movement, فيحصل الانرجي اللي كان الكاينتيك انرجي يتغير حالها من السرعة من الكاينتيك انرجي إلى حاجة تانية, which is usually heat, correct? Now what happens here? You have a very fast electron going extremely close to a high energy area, which is close to the nucleus. إيش يسوي؟ يقحص. It changes الاتجاه حقه تماماً, and it completely loses all its energy. In energy الناتجة عنها is an electromagnetic energy, which is a photon. And actually, the word Bremsstrahlung, هذه الكلمة بالألماني معناها تفحط, basically. So let's look at it one more time. You have an electron, it goes through, it completely changes الاتجاه, and all of the energy of that electron changes into a photon. And this is the main source of radiation. The second type of radiation that is produced is something called characteristic radiation. And let's take a look at the production of characteristic radiation. So let me bring this one up, and I'm going to change the sharing screen to something else. All right, quick play characteristic radiation. All right, share. Okay. So here's a new one. Thumbs up if you can see it. Thumbs up? Yes? Yeah, okay, perfect. All right. So now, أبغاكم تركزوا. Again, now you're going to have an electron coming in من برا. Okay? Now I want you to take a look and see what happens to this electron. So here it comes. What happened here? So what happened here? This is another type of radiation that is produced, but it also produces a photon. So let's take a look at it one more time. Electron comes, kicks out another electron in the inner shell, very high energy. An electron from a less energy shell comes back. الفرق بين التو energy, الفرق بينهم يحصل إيش? A photon. Okay, so in characteristic radiation, what happens is تعريفها إنه an electron comes, kicks out an inner electron. مهم جدا, an inner electron, because they have very high energy, right? That one is kicked out. طبعا الاتم ما ينفع يقعد with an inner electron missing. فعلى طول يجي مكانها another electron. الفرق بين ال two shells, الانرجي shells, يطلع a photon. لأنه remember, energy يتغير الفورم, لا يتلاشى ولا يخلق من العدم, right? It changes form. So this السرعة دي will kick another electron out, create another electron that comes down from a lower energy place, والفرق بينهم يحصل photon. This is the production of X-rays. Okay, so let's go back to our presentation. Here it is. Okay, so if we go back here, what you're going to see is the production of X-rays happens when we boil off electrons from the filament. That will then interact with the tungsten target in two main ways. The two main ways are the Bremsstrahlung radiation, where an electron will come in very, very close to the nucleus. It will change its direction and lose all of its energy, and that energy is turned into radiation. That energy is turned into photons. The other one is by an electron kicking out an inner electron, and the difference between an outer electron and inner electron, becomes radiation. That's how these little bundles of photons are produced when these electrons hit the target. I hope that's clear. Now, what are the controlling factors when we are creating these X-ray photons? في أشياء معينة that إحنا نقدر نتحكم فيها as users. أول حاجة اللي هي التوب voltage. التوب voltage, I think I have one by one afterwards. No, I don't. We're going to talk about this بالكلام. If when inshallah you use an X-ray tube for your patients, usually you have like a little board where you're going to press the button and take an X-ray. Okay, بس هنا حيكون عندكم different factors تتحكموا فيها. واحدة منها اللي هي tube voltage. The other one is your tube current, and the other one that you can تتحكموا فيها is tube exposure time. Now, tube voltage is the energy of the X-ray tube. زي ما قلنا, the energy of the X-ray tube is the X-ray tubes تسوي شيئين, يسوي الهيتنج ويسوي البوتنشال. فأنا لما أزود التوب voltage, لما أغير التوب voltage, أزوده أو أقلله, أنا قاعدة أزود أو أقلل من الانرجي. فإيش يصير؟ When I increase the energy, I am technically increasing the energy of the electrons. فالإلكترونز اللي هي was formed on the filament, أنا لما أزيد التوب voltage قاعد أزيد سرعتها, فأنا قاعد أزيد من الانرجي الفوتونز الناتجة عندي. Okay? So what happens when I have a higher energy photon? Usually a higher energy photon will result in a photon or an X-ray that is more penetrating inside the human body or whatever I'm trying to image. وإحنا حنتكلم على هذه الأشياء بعدين. ليش مهمة إنه أزود penetrability أو أقلل من penetrability of the tube. فهذه أول حاجة. ثاني حاجة current. Now كلنا نعرف X-ray, كلنا نعرف إنه electricity فيها current, and we call it the MA, milliamperage of electricity. طيب, يعني زي ما مثلا الواحد عنده لمبة, صح؟ ممكن أزود milliamperage أو أقلل من milliamperage حقتها, صح؟ فالمليامبيرج يعني أي جهاز, عندك توستر, مايكروويف, whatever, ممكن أزود وأقلل من milliamperage. Now in an X-ray tube, لما أزود milliamperage, أنا قاعدة أزود current of electricity. Okay. لما أزود current of electricity, أنا إيش قاعدة أسوي؟ أنا قاعدة أزود من عدد electrons that are produced on the filament. حلو؟ أزود current, قاعدة أزود عدد electrons. فكروا فيها كده كأنها زي الموية. لما current of the water, مجرى الماء, لما أزود current حقها, أنا قاعدة أزود كمية الموية. لما أزود current, قاعدة أزود كمية electricity. لما أزود كمية electricity, إيش قاعدة أسوي؟ أزود من عدد electrons اللي is boiling off, وبالتالي قاعدة أزود عدد الفوتونز الناتجة عني, أو قاعدة أزود the amount of X-rays that I produce, not the energy. أنا قاعدة أزود العدد. See? So why is it important? It will be important again. There are some cases where I need to increase the number of photons that are required to produce an image. Not the energy of it, but the amount. أديكم مثال كلينيكي يعني. Let's say عندي أنا هاخد X-ray على طفلة صغيرة versus هاخد يعني X-ray على راجل كبير كذا معضل وكذا يعني buff مثلا. The number of X-rays I need to produce the image in a small child versus this person is very different. For a child, I need a lower number of photons to produce a diagnostic image versus a big buff guy مثلا, I will need more number of photons to produce an image. This is where the clinical connection is. فأنا أقدر أزود milliamperage أو أقلل milliamperage depending on the patient density. The other thing which is really important in dentistry, depending on what site I'm going to be imaging. Let's give an example. Mandibular molar area is a lot thicker and a lot chunkier than the central incisors in the maxilla, which the bone is thinner, the teeth are smaller. فأنا أغير الملي amperage ما بين الانتيريور والبوستيريور عشان يكون عندي image حلو. If I use too much radiation, ممكن يكون I get a very dark, overexposed image. Versus if I'm using I need less amount of radiation مثلا in a smaller area. فنغير الملي amperage depending on the density. Higher density needs more photons, lower density needs lower amount of photons. طريقة ثانية إني أنا أغير من the amount of radiation produced, the amount again, right? Is by changing exposure time. So time of exposure, يعني قد إيش أنا ماسكة الزرار قاعدة I'm producing X-rays. حلو؟ It is أنا فأنا لو زودت time of production, right? راح أزود عدد الphotons that are being produced. So whenever we think about milliamperage لما نتكلم على current واتكلم على time دائما نتكلم عليهم مع بعض. And that's why we call it MAS. يعني milliamperage times the time. Okay? أديكم مثال. Again بالماء with water. أنا لو عندي هوزين ماء okay وعندي 2 buckets وحزود فيهم المويه. في طريقتين إني أنا أفرق بين الاثنين. أنا لو ثبت الكرنت يعني الكرنت حق الموية فتحتهم على الصنبور على نفس القوة أوكي؟ بس قفلت واحد قبل الثاني مين حيكون فيها موية أكثر؟ أكيد الباكت اللي أنا يعني كان التايم أكثر صح ولا لا؟ Now خلينا نثبت التايم. أنا حثبت التايم to 3 seconds بس كل واحد حفتحه على قوة ثانية. واحد حفتحه على الآخر وذي other one حنقط بس شوية البريشر. أكيد اللي فيه البريشر أكثر حيملي الباكت أكثر من الثاني صح؟ So whenever X-ray production is the same exact thing. What we do is we change the milliamperage and we change the time depending on what we want to produce. Usually dentists in their practices are able to change the time and not the milliamperage. بعدين لما ندخل في اشياء تانية زي الكون بيم وهذه الاشياء عندنا القدره انه نغير الاثنين بس انتوا everyday practitioners what's going to happen انه تقدروا تغيروا time and not the milliamperage. So for a child مثلا حزود التايم of حقلل من التايم of exposure. For an adult حزود التايم of exposure. For a molar حزود التايم of exposure. For the anterior teeth which are small and lead nest radiation حقلل من التايم of exposure. So those are all the little things لما نفهم الفيزيكس أقدر الحين أفهم أنا ليش بسوي أشياء in the clinic, right? So this is a summary of the things that are going to contribute to the energy and the amount of radiation that are produced. Tube voltage will change the energy of your beam. Tube current and tube exposure time are going to increase the amount or the intensity of your beam and not the energy of the beam. في أشياء تانية تأثر which is something called filtration, collimation, and inverse square law, and let's look at that. The first thing is filtration. So when our X-rays are produced from the target, what we do in all of our X-ray machines are something called filtration, where it's an aluminum filter, where أشيل كل low energy X-rays that were produced وما أحتاجها. أنا أحتاج high energy فقط لأنه low energy photons اللي is resulting, all it will do in my image is just create noise. ما نحتاجها. فأنا بنعمل filtration. كأنه بالضبط بنسوي فلترة للفوتوز حقتنا. لو what we're going to do is remove all the low energy that is going to create noise. Okay? And this is built into your X-ray tube or your X-ray machine. And they call it an aluminum filter. Okay? The second thing that we're going to do is something called collimation. Collimation is also available in your machine. لما حاجة اسمها collimation يعني أنا أقلل amount of radiation اللي طالع بس للarea of interest. لو أنا مثلا في يعني X-rays for أسنان بس حسوي مثلا للضرس. لو أنا حسوي collimation for a chest X-ray I'm gonna أزود الcollimation حقي، فإيش يصير؟ for the entire chest is going to be exposed. فcollimation is كأني مثلا أنا أخذت الكاميرا أنا zoomed in أنا zoomed out بس عشان أصور المكان اللي أنا أبغاه أنا use the photons في المكان اللي أنا أحتاجه. Now, inverse square law is a law that you'll read about in books, which is the intensity of the X-ray beam, which is intensity. دائما لما تسمعوا كلمة intensity معناتها the number of photons. إنزين؟ In number, not the energy, number. So the intensity of the X-ray beam, meaning the number of photons, okay, per cross-sectional area per unit of exposure time depends on the distance of the film from the focal spot. يعني أنا كل ما بعدت my film or from my receptor from the X-ray source كل ما حيقل عدد الفوتونز اللي جاية على هذيك المنطقة. ليش؟ لأن الفوتونز كل ما تبعد كل ما يوسع مكانها زي الكون. أديكم مثال، لما يكون عندكم فلاش لايت، حلو؟ تفتحوا النور الفلاش لايت. أنا الفلاش لايت لو حطيت الفلاش لايت على حيطة الانتنسيتي of the light عند الحيطة حتكون very strong لو حطيتها قريبة من الحيطة. Now, wait. Now, if I go back, إيش هيحصل؟ صح هيزيد ال area of exposure بس the intensity of the light is going to be much less and much less intense غير لما تحطوها قريبة جدا من الحيطة. The same thing as X-rays. ترى X-rays are very similar to light. The only difference is one penetrates the body and one doesn't. But it's the same concept. فكل ما بعدت, so this is the inverse square law. كل ما بعدت عن الفيلم كل ما intensity of the photons حتقل أو عدد الفوتونز في المنطقة هذه حتقل. That's the only thing you have to understand. وهذه لها تطبيق كلينيكي إنه إحنا what we try to do as much as we can لما نحط الفيلم نحطها أقرب شيء على الفيلم وما نبعده كثير عن البيشنت، لأنه اللي حيحصل لو بعدته كثير عن البيشنت the intensity الإيمج حقي is going to be very underexposed very light ما راح أشوف شيء. right؟ فالتطبيق إنه إحنا أقرب as much as I can to the receptor or to the film. Okay? All right, so this is just a summary of what I just said. The current MA, MAS, the current and the time زي ما قلنا إحنا دائما مع بعض current و time ما ينفع نتكلم على واحد غير الثاني. All right؟ لأنه لازم واحد يتثبت وواحد يتغير. أو نزود الاثنين أو نقلل الاثنين فلازم مع بعض. So current MAS milliamperage per second, an increase in quantity and no change in quality. Kilovoltage will increase in the quantity, in the quality and not the quantity. هنا الquality هذه مشبوهة بس أنا لو تحفظوها مني voltage will increase the quality and not the quantity. Added filtration, it will decrease in quantity حيقلل شوية من العدد بس it will increase the quality of the image. يعني low energy صح عدد الفوتونز حتقل بس حتقلل من الانرجي اللي احنا ما نبغاها فيجينا good quality X-rays. Alright. هننتقل الآن من مرحلة forming photons. خلاص خلصنا منها. Alright. So هنا in the X-ray tube we created photons and now we've created an X-ray beam through all of those mechanisms and all the things that we talked about here. What's the next step in our radiation or in our X-ray in our X-ray sort of journey? The next thing, this is what's going to happen, is that these X-rays or these photons are now going to interact with the body to produce an image. Now, this is what we're going to talk about, the interaction of X-rays with the body to produce an image and how that happens. So, interaction of X-rays with matter. So, what happens? الحين خلصنا من هنا الphotons دحين. This is what we're going to be talking about. Here is your X-ray tube. It created something called an incident beam, which is البيم اللي طالع من من الماشين بانرجي معين بكوانتيتي معين بكواليتي معين. حلو. It then hits the body, right, and interacts with the body, ويطلع من الجهة الثانية حاجة اسمها attenuated beam. يعني البيم now interacted with the body ويطلع من الجهة الثانية البيم carrying all the information I need to hit the film to give me an image. احنا دحين حنفهم الاكس-راي beams هدول ايش حيحصل هنا عشان to create an attenuated beam. So, what does beam attenuation mean? The total reduction in the number of X-rays remaining in an X-ray beam after penetration through a given thickness of tissue is called attenuation. Now, أنا جاية beam قوي, right? It's going to hit the body. طبعا it's going to interact with the body. فعدد الإكس-rays حتقل والenergy حقها بعد ما كان سوي كله مع بعض. Now حيختلف الenergies صح من الجهة الثانية. الاختلاف الenergies هذه is then going to be captured onto a film, and that's what's going to produce your film. Okay, so the interaction of the X-rays with enamel is going to be different than its interaction with dentin, is going to be different than its interaction with pulp, different than its interaction with bone. وهذه الفروقات اللي حتعطيني an radiographic image or an X-ray image. This is a product of absorption and scatter of the X-ray beam related to that particular part of the body that you're imaging. So how does that happen? We have 3 different interactions. We're going to look at 3 different videos right now. طيب بس remember احنا كنا الفيديوز الأولى عشان لا تلخبطوا بس عشان شكلها زرقاء. Okay, لا تلخبطوا. The first one that we looked at was the electron interacting with tungsten to produce a photon. Now we're going to looking at the photon interacting with an organic molecule in the body or non-organic, whatever it is, interaction of the photon with the body to produce another photon that will carry information to the film. Okay? All right. There are 3 types of interactions. The first one is what we call the photoelectric effect, and this is the most important effect that will produce an image for us. The 2 other ones are called scatter, cohort scatter, and Compton scatter. These are what cause a little bit of noise, and that's why we never have a perfect image ever. دائما في كذا غلاسة فيها scatter. But this one is going to be your most important, the photoelectric effect. So let's take a look at the photoelectric effect. All right, here we go. So I'm going to put up the photoelectric effect, and I will change my sharing to the photoelectric effect. Time, photoelectric, here we go. Okay, share. All right, if you can see it, give me a thumbs up. All right, perfect. Okay, so now I want you to take a look at this. Now what you're going to see, instead of an electron coming in from the side, you're going to see a photon coming in through the side. Okay, now let's take a look and see what happens. Here's your photon. All right, so let's take a look at that one more time. Photon comes in, it kicks out an inner electron and is completely absorbed into that, and we get a secondary electron that comes out. Okay, so what happened here? Basically, what happens here is that the photon is absorbed by a certain tissue. It completely gets absorbed, and an electron is kicked out. طبعا, this causes ionization of this particular atom, and that's why we always call this type of radiation ionizing radiation. يعني, and it's penetrative. So it ionizes these atoms. بعدين, in another lecture, we'll talk about the biological effect of radiation on the body, but we're not going to talk about that today. But what happens here, this is completely absorbed into this particular atom. فاللي هيحصل ما هيطلع بدالها any kind of photon. It is absorbed. فإيش صار? You had a beam coming in with a certain number and a certain energy. One of those is going to be واحدة منهم حتتلاشى حتروح. It's absorbed مثلا by enamel or by dentin. Okay? So let's take a look at the other types of absorption. So this was the photoelectric. Now let's go to cohort scatter. Cohort scatter is another way that your photons will okay, here we go. Cohort scatter. Here we go. Share. Okay, so now we're going to look at the cohort scatter. Let's put play. Your photon is coming in from the side. And what it does here is that it نفسها بالضبط. It hits an outer electron, يتغير اتجاهها, and it scatters. And that's why we call it a scatter. لأنه إحنا ماشي الفوتون باتجاه معين. Now it hit an electron وتغير مكانها ونزل. This doesn't hold a lot of information because this is what we call scatter. It just scattered away and ما أخذنا منها حاجة. Now let's look at characteristic radiation, which is, nope, Compton scatter. Sorry, no characteristic. We did cohort. Now we're going to do Compton. Right. Sorry, Compton. Share Compton scatter. Okay, share. Here we go. All right, another photon is coming here. And now look at what this photon is going to do. It kicks an outer electron, and again, يتغير اتجاهها ويقل الانرجي حقتها. ليش؟ لأنه الإلكترون اللي طارت أخذت جزء من الانرجي حقها عشان تتخلع من مكانها. Right? فتغير الانرجي وتغير الاتجاه. في الثاني ما انشال الإلكترون. ليش؟ لأنه was a hardly binding electron. It wasn't enough. So what happened? بس اتغير اتجاه. Okay? So these are the three ways that photons interact with the body. Let's go back عشان نشوف الموضوع ملخص. Okay, so here you had the photoelectric effect, the cohort scatter, and the Compton effect or the Compton scatter. So let's just look at this بطريقة يعني منظمة شوية. Photoelectric effect is basically where the energy of the incident X-ray is the electric binding energy and the kinetic energy of the electron. So what happens is that it goes in and it affects and it's completely absorbed by this particular atom. With the Compton scatter, what happens is just one of these electrons are removed ويتغير اتجاهه ويتغير الانرgy. So when we look at how X-rays interact with the body, 27% of your photons are going to interact as a photoelectric absorption. And the Compton scatter is going to be about 57%. And that's why we have a lot of a scatter with X-rays. Some will have no interaction at all. And then 7% you'll get a cohort scatter. Now, why is this important to understand? It's important to understand لأنه المعلومات اللي حتطلع من الجهة الثانية يعتمد على the differential absorption of different tissues to your X-ray beam. Very dense tissues will completely absorb your X-rays, right? وحيطلع الجهة الثانية نقطة بيضاء, okay, which is radio opaque. يعني لما تشوفوا enamel مثلا, which is the most radio opaque thing that we have in our bodies, هيطلع دائما بيضة. ليش؟ لأنه it completely absorbed the X-rays. ما في ولا شيء مكانها. Dentin is a little bit less dense than enamel. فإيش يكون؟ الابزوربشن حقه يكون شوية أقل. فيصير في difference ما بين الراديو اوبيك enamel والراديو اوبيك dentin لأنه في فرق بين الابزوربشن. بعدين لما نشوف soft tissue، السوفت تيشو تقريبا الاكس رايز تمشي فيها بدون أي حاجة تقريبا، فيديك شيء لون شوية grayish. فالفرق ما بين الabsorption of these X-rays through the body will give you that differentiation and give you those shades of gray. With completely no interaction being black، معناه إنه كل الX-rays مشيت through it زي air مثلا in the sinus and hits the receptor زي ما هي فيطلع لون أسود. تخيلوها زي الإنك مثلا، زين؟ الفوتون دي عاملة زي الإنك، تطلع على جهة ثانية تصير سوداء، لوناها right. فالأسود معناه radiolucent، يعني ما كان في شيء يوقف في مكانه. أي حاجة فيها shade of gray أو بيضة معناته إنه وقفنا الإكس رايز وهي ماشية. complete مثلا حتشوفوا amalgam fillings، حتشوفوا crowns، حتشوفوا endodontic restorations مثلا gutta-percha. كل هذه الأشياء will absorb your X-ray beam ويطلع الجهة الثانية مكان أبيض ما نحط عليه إنك، يطلع radio opaque أبيض right. So if we look at that, I think I have it here. So if we look at this in real life, these are your teeth, here is your gingiva and in bone. فلو طلينا وشفنا هنا وفكرنا في الفوتونز اللي ماشية في البار اللي جات originally كلها energy واحدة وكمية واحدة and it hit these tissues، هتيجي الجهة الثانية بطرق مختلفة. هنا you have an amalgam filling. The amalgam filling completely absorbed the photons, giving you a white patch right here. These are fillings. Here is enamel. Enamel is the next most radio opaque thing. فهنا you have absorption also giving you enamel. Then you have dentin, which is a little bit less dense than enamel, وفيها soft tissue صار في أقل. بعدين هنا طبعا pulp is complete soft tissue فهتلاقوها أقل بعد. بعدين هتلاقوا هنا air، هذا this is the oral cavity، مشي فيها الفوتون زي ما هي وطلعت وحطت لك منطقة سوداء هنا. Okay? So the differences between the absorption are going to give you this difference here. Here you have trabecular bone, where you have bone plates and bone marrow. Again, you're able to see those differences based on the absorption of these photons. And that's basically how we create an image. Okay? So if you guys have any, that is basic physics, basic understanding of the production of radiation, basic understanding of how X-rays are produced, how they interact with the body, and how they actually create an image after all of that. So before I close the recording, if anybody has any live questions, I'll be more than happy to answer. And for the people that this is recorded for, please do ask me any questions on our WhatsApp group. I'll be more than happy to answer. So if anybody has any questions, please jump in and ask. If not, then inshallah بكرة نفس الوقت الساعة 10 I'm going to be continuing our radiology series, and we're going to be talking about intraoral radiographs, which is the most important radiographs that the most important radiographs that you take as dentists. And yeah. Okay, يعطيكم العافية للي حضروا, and hopefully whoever, oops, I have a chat here, I didn't see. What is, somebody asked, what is the energy transfer process? So the energy transfer process, you mean the energy transfer process from the from the body to the film? Am I getting that correct? I think it's Hiba, صح بتسأل? What is the LET, linear energy transfer process? Yes. Okay, the linear, I mean content scatter. Okay. So first of all, both questions are good. So the linear energy transfer, which is the LET, linear energy transfer. LET is something that we use for measuring the transfer of energy to anything using radiation. And this could be مثلا, and usually we use it to compare different types of radiation, ionizing radiation specifically. So X-rays, gamma rays, uh, alpha rays, different kind of rays. So نقارنهم how much energy transfers into the body because تختلف ما بين different types of radiation. In diagnostic radiology, we're only use, or in dentistry specifically, we're only using X-rays. We don't use the other ones. It's not as important. But so when it comes to Compton scatter, both types of scatter, both types of scatter, what happens is إني أنا عندي فوتون ماشي باتجاه معين بانرجي معين واللي يصير ان it hits the body, or it'll, let's say it hits any part of the body and then it scatters to somewhere else. That scatter to somewhere else, if it is a low energy where it loses energy, it's going to be absorbed somewhere else in the body ويطلع منها بدون فايدة, right? ما استفيد أنا من السكاتر هذا. Now الثاني اللي تغير اتجاهه but it had enough energy to leave the body, and now it's going to put a dot, or it's going to put a piece of information of my film that really doesn't represent anything, right? But that dot on the film is going to look like noise, or it's going to look like what we try to do as much, we can't get around it, but what we try to do as much as we can is to decrease these kind of scatters as much as we can, but sometimes we really can't. And that's why we never get a perfect picture. But yeah, very good question. Very good question. Anybody else before I finish off the Zoom? Okay, tomorrow hopefully I'll have my presentation proper. I'm gonna I jump back and forth between stuff. And tomorrow we'll be talking about again زي ما قلت لكم intraoral radiographs, periapicals, and bite wing radiographs. And we're going to be watching a video together. Through that video, we'll discuss it, because I know the best way to do this is to do it in person on a simulator or on a patient. But till that day, we'll do it on a video, which is very, very useful. So I will see you guys tomorrow, 10 o'clock. All right. Thank you. والله hearts عليكم كده كلكم كده big fat hearts. Allah.